Alrighty, so for this video we're going to do chapter 6 basically. Excuse me. Really the idea of chapter 6, they're all basically the same thing. It's not all of chapter 6, we're just doing chapter 6.1, 2, and 3. Which may seem like a lot at one time, but it's not. Because what's going to happen is 6.1, you're going to be given a system. It's a nice easy system. So something like this. And something like this. And I didn't make the, I just made this up just a second ago as I'm, well, right this instant. So I have no idea what the solutions will be to this guy, what our eigenvalues will be. But the eigenvalues determine what kind of solution we have, okay? And what we want to know is, can you describe just from the eigenvalues how x and y relate to one another? In other words, x and y do their own things, but they're obviously tied together in some fashion. And if you were to graph them, because remember x is a function of t, and y is a function of t. But if you were to graph it such that y is here and x is here, what would they do? Okay, so it could be a situation where they orbit this steady, this steady state solution like we talked about, right? So we've already talked about a lot of this stuff, but so we're just going to kind of hit this again really quick, look at some graphs of some phase planes, and then just kind of keep moving along, okay, throughout the thing. So again, we've done a little of this, but just kind of bear with me here. So, and then, or it could be a situation where it's here and it kind of starts to spiral out, All these things be determined by our eigenvalues, okay? Oops, back to that page. So our eigenvalues on this one, of course, are 3 minus lambda, 2, negative 1, 1 minus lambda. So that's going to be it doesn't factor. So 4 plus or minus the square root of 16 minus 20 over 2. So 2 plus or minus, that's 4, so 2i. So 1 plus or minus i. Okay, so because it's complex and because this dude is positive, we know it's going to start here, it's going to spiral out. Okay, it's going to be a spiral source, right? So we've talked about some of that. And I don't need to really berate the point any further than that. It is what it is. Now, I'm going to pause you for a second while I pull up a new phase plane plotter. So it's this one here. Found this one. It actually is not too bad, I don't think. And so my function was, I forget, hang on, was negative 3x plus 2y. And my y is negative x plus y. What? Weird. What's going on here? All right. So, we can zoom out, of course. We can change these. Notice how nothing really changed a whole bunch on that? And nobody's terribly shocked by that, I don't think. Now, I wonder where my center is on this guy and what sort of deal it is here. Now, we said it should have been this thing here, okay? But if you think about it, what values of x and y would cause this to be, to have these guys be equal? Because that's where our equilibriums are located. And so, as you can see, it would be 0, 0. Interesting. I wonder if I zoomed in a little tighter actually on 0, 0, say negative 2, 2. Oops. Come on, graph it, piece of garbage. Why are you doing this to me? Why do you hate me? Alright, so let's, when all else fails, get your calculator out. Double check your eigenvalues are right. It's been a long day. What do you want to bet? I got the wrong. God dang it. Do it again, dummy. Okay, it's 2 plus or minus I, so that's helpful. Alright, let me pause you for a sec. Alright, so in yet another way, and I was going to show you this one too, but I guess I'll just do this one. The other one is not wanting to function, and that's kind of irritating me. But whatever, I guess. String plot. What you can do is type in the functions you have. So 3x plus 2y, comma, negative x plus y. Alright, and then you're going to go comma, x, and then let's go from negative 2, dot, dot, 2, comma, y, let's go from negative 2, dot, dot, 2. If you do this, there it is. And pretty clearly, I think you can see at 0, 0, we have a spiral source. Okay? Which is kind of what the game was supposed to show. Alright, so then again, you know, you try another one here, let's say, and you think, well, okay, I want to try. Get off of there, you hippie. I don't know. So x prime is 2x plus y. Y prime is equal to, wait for it, dude. Oops, plus 2. Wait a minute. Now, if I set these babies equal to 0, oh, well, they're not going to equal 0, 0 at 0 anymore. They're going to be, you know, well, different. So in other words, a person could, if you wanted to, just take this guy, set equals 0 like it is, and then this guy is this, yes? And then if you add, you just get 3x is equal to negative 2. So x is negative 2/3, which means that y add that over there, you're going to get negative 1 1/3, so negative 4/3, I think, is equal to negative y, so y is 4/3. So negative 2/3, 4/3 is what everything's going to, I don't know if it's going to orbit around it, or it's going to decay to it, or blow out from it. Who knows? We'll find out in a moment. So what we need to do is, we need to find our eigenvalues. Now you're like, wait a minute, this I get, no problem. This I get, no problem. Sure. What goes here? That's weird. Okay, well, here's what we're going to do. This is what we're going to do. We say this one is, well, it's almost linear. Literally, that's what it's called. Almost linear. In fact, it is linear. But the idea is this. What you're going to do is you're going to do partial derivatives. So, not dy dx. Sorry. So what you're going to do is you're going to take the derivative, the partial derivative of that first function up there. Okay? So you take the partial derivative of this guy with respect to x. Okay? So of x prime. I'll write it like that. And then you can take the partial with respect to y of x prime. And then what? You're going to take the partial with respect to x of y prime. And what you're finding here is, in essence, how these things are behaving in a linear fashion. Now take the derivative of this guy with respect to x. You get 2. Weird. Take the derivative of it with respect to y. You get 1. Weird. Take the derivative with respect to x on the bottom, you get 1. Take the derivative with respect to x on the bottom, or with respect to y, you get negative 1. But what happened to the 2, you say? Well, is it changing anything? It sure is not. So it's not part of the change, it's just there. So then you're like, well, oh, so all I have to do is this thing again? Yep. Ouch. So you're going to get plus 2 minus 1 no, that's minus 2. Plus 1 is negative 1 lambda. Minus 2 minus 1. So I think it's this, which doesn't factor, so I think it's going to be 1 plus or minus the square root of 1 minus a plus 12 or 2 or something like that, I think. I'm going to whip out the calculator right now because I don't want to mess with this anymore. So I'm going to just pull this out. Alright, so there they are. 2.3 and negative 1.3. So remember, what our functions are going to look like is e to the 2.3t and e to the negative 1.3t. Well, in both of them, so there's going to be some constant here plus some constant e to this, a different constant e to this. And because they're equal, because they're opposite signs, what's going to happen is we're going to have a saddle point. So again, come over here to our this deal, and we need to, I think my equations were 2x, and I don't remember, 2x plus y, and this one was x minus y plus 2. Oh, dude, look, it's a saddle. That's classic saddle. And where is it happening? Negative 2/3, comma, 1-ish. Yes, or 4/3, which is what it was. Exactly right. Okay, pretty cool, pretty easy to do. Not too bad. Now, what if you run across one that's quote-unquote a little less linear? What if it was some nasty mess like this? That's not the messy part. I don't know. Okay, well, first order business, it'd be kind of cool to find out where they equal 0. And I don't know where they do, and matter of fact, I'm pretty sure it's 0, 0, but I'm going to put a -1 here just for grins on the bottom one, just so maybe it's not 0, 0, because that would be really boring. So I'm going to go solve. I'm going to go 3x minus, and you have to do x times y, don't forget, plus y squared. I'm going to solve that equals 0, comma, or not comma, and, so second math. And then 2x squared plus y minus 1 equals 0, comma, brackets rather, x comma y brackets, parentheses. Wouldn't be surprised if there was a couple of them. Betsy's taking her sweet time solving it, so that's always fun. There they are. So there's that one, negative 0.3 and 0.8, or negative 1.38 and negative 2, and this is 2 of them. So I'm going to jot those down before I forget them. So negative 1.3 and 2.8. That's one of them. And the other one is negative 0.3 and 0.8. Okay. Interesting. Okay, so let's make our determinant, if you will, and see what happens with this deal then. You're like, okay, well, I can do partial derivatives. That's going to be 3 minus y, right? And then this is going to be, with respect to y, it's going to be negative x plus 2y. With respect to x, it's going to be 4x. With respect to y, it's going to be 1. Nice. I'm going to put that there just for grins, and then minus lambda. I'm going to do that in a second here. But you're like, what am I going to do? Well, one at a time, you're going to drop those dudes in for your x's and y's. Nice. Now, again, I'm a little lazy, so what I'm going to do is the following. Oops. Okay, I'm going to make myself a new matrix, and I'm going to put it in just like this. I'm going to do 3 minus y minus, I'm going to put z in for my lambda, okay? Now, there's a reason why I'm doing that. I'll show you why in a minute. Minus plus 2y, and then 4x, comma, and then I'm going to do 1 minus z. And what I'm trying to do is I'm trying to automate this sucker. Yeah, I really want to automate it. I want this to be as easy as I can make it to really make myself, you know, have some pretty cool things going on here. Now, in fact, that's how I would do it if I was doing it by hand. So let me just back up the train a minute. What I'm going to do is I'm going to plug negative 1.3 into there. Or I'm sorry, for y, I'm going to plug in 2.8. I'm going to plug in 2.8 here, and I'm going to plug in negative 1.3 here, and negative 1.3, and I'm going to plug in. That's it. And then I would do it by hand. I would get like 0.2 minus lambda, 1 minus lambda. You get the picture, and then it's going to be 1.3 plus 5.6 is 6.9 or something, and then I'm going to get negative 5.2 or something, and then I would do my thing from here. Okay. The calculator doesn't need that, okay? So I kind of got a little ahead of myself. I don't want to put the z's in there because those were my lambdas, okay? I don't want to put them in there. Boom. So what I'm going to do is I'm just going to go such that x equals negative 1.3. And then I'm going to do such that, I'm going to clear that. I'm going to grab this guy and I'm going to go such that y equals 2.8. So I can speed this process along, and all I have to do is go, all right, second value eigenvalues, because that's what I really want to know. And there they are. Well, look at that. It's positive 0.6 and then an I. So this means this is going to be a spiral source. Okay? Now I come back and I do it again. Back to the original, which is this one. Bring it down, get rid of this, and then just put in negative 0.3. Clear, grab this guy, such that y equals 0.8. And then let's just do the old eigenvalue Rooney on that feller. And it is also a spiral source. Okay? So let's go look at that and see if we believe that's true. So there's our function. So it's going to be... I have a keyboard. Where'd my keyboard go? It's going to be 3x minus x times y plus y squared. Comma. And the other one is 2x squared plus y minus 1. Oh, dang, I did negative y plus 1. No, is that right? Yeah, it's supposed to be positive y minus 1. Well, if you don't type it in right, it's funny, you don't get the right answer. It's weird how that works. Okay. Now, again, where did these things occur? They occurred at, what did we say? Negative 1.3 and 2.8. So negative 1.3 and 2.8. Negative 2.8? No, positive 2.8 it says. Okay, so that's a little weird. Maybe I wrote that down wrong. That could be part of our issue. And then there's a spiral source clearly at where? So basically the other one. So negative 0.3, positive 0.8. And that looks about right. So the other one, I bet I wrote it down wrong. So let's go look at the stupid calculator, see if Jay wrote it down wrong. Well, that's annoying. I lost it apparently. Didn't I say solve? Oh, for goodness sakes, get to the bottom. Apparently I wrote it down wrong, so let me just check it. Now, according to my graph anyways, it should have come out, differently, of course. So I just want to make sure that we typed everything in right. I don't on purpose make mistakes. I make plenty without trying. So I feel like I give you enough what ifs without trying to make mistakes. So when I make a mistake, you can be sure that it happens. These things happen when you're doing them. Come on, give it to me. Yeah, it must be a blah blah. It helps you use an equal sign, dummy. Worthless calculator. I don't know why you can't solve it. I bet you it's going to be -2. It's going to be something. I don't know. Let's go see. So there's the first one. I bet I wrote the other one down wrong. -1.3. -2. Well, for God's sakes, what do you know about that? I put in +1.3. And -2.8. Right? There you go. Big dope. So that means that's probably going to change, yes? So let's go look at that again. So let's go and just see what happens to this guy. So, clear. Scroll back up here a ways. Scroll back up here a little further. A little more. Right there. And let's put in this -1.3. And let's take that answer. Let's try this again. God, I'm an idiot. Such that y equals -2.8. Alright, and then clear that, and then go second math 5, 9 eigenvalues. What do you know? They're opposites. That means it's a saddle, which is exactly what the picture shows. What do you know about that? If you do it right, Jay, there it is. Bam, there's your saddle going on right in that mess. Okay? Alright, so that's probably the easiest way to do it is this stream plot business. I'll show you the other one maybe in another video. There's another one that's kind of cool. It's okay. I don't know if it's... I don't know. The other one worked just fine earlier, and now I don't know what I'm doing wrong with it, but I'm not going to fool with it anymore either. Meaning by that. Now, that is section 6.2 is these other ones that are basically almost linear, where you're going to have to do derivatives in order to find them. Okay, so it's not hard, it's just something a person has to do. I'm going to do one more example of those, like this one that I just did, but of course, you know, different, because why not? So this one comes to mind. It's xy minus 2, minus 2 is your x prime, and your y prime is x minus 2y. Alright, so again, when I set them both equal to 0, that's the whole point. I want to find out where those happen. Alright, cool. Now, it's possible you can dink around and solve these. I don't dink with these. I just go right to calculator. Yeah, there's zero reason to do it any other way, unless a person were to use Desmos and see where they crossed. And that's totally hunky-dory with me, too. Where are you, Desmos? That's weird. All kinds of weird stuff, but no Desmos. Desmos.com. So they are xy minus 2. And x minus 2y equals 0. It's funny, a gal I work with at work the other day, she was just beside herself because she just figured out that kids can just type in functions like that and they'll put on there. I go, yeah. Well, I'm like, you just got to write a better quiz. That's all, better tests. So keep an eye on things better. But you know, yeah. So -2, -1, and 2, 1. So here are where we have some equilibrium positions. So the question is, what kind of equilibrium? And the idea is, are they stable or unstable? The only kind that we're going to have that are stable are going to be, you know, that are going to be the stable centers. Or in the case of everything is coming down to a, you know, everything's coming into it, like so, yes? If there's things going that way, we'd have an equilibrium where everything was converging to it. Okay? But the idea is, what are we going to have here? Saddle points, what are we going to have? You know, I don't know. So what is the derivative of this with respect to x? It's y. And with respect to y, it's x. And the bottom one is going to be 1 and -2, right? And again, if you're doing this That's how you play the game. Okay, and then you just take turns plugging these guys in. So that's going to be -1, -2, like that. And then I just break out the old calculator and ask Betsy to find eigenvalues of that guy. And, do what you want. Maybe you just prefer to do like I do and just come here and edit, because I find sometimes that's easier than typing it all in again. And you're like, well, last time couldn't you just type in with the y's and the x's? I could. This one seems easier to do it this way. So -1.5 and an I. So this guy is a spiral sink. And let's plug 1 in. It's going to be 1 and 2. And that's still -2 already. Ooh, saddle. So xy minus 2. Oh, baby! Saddle. Saddle, do you see it? Look at it. And there's my spiral sink. Nice. Just like we said it should be. Enough of this foolishness. Now, into the next section we go. 6.3 is just what it called ecological models. But if you want to think of them as predator-prey models, that's really all they are. Nothing too exciting about them. For instance, here's one of them. dx dt is equal to 5x minus x squared minus xy. dy dt -2y plus xy. Nice. Okay. So then again, the idea is set them equal to 0. Find out where they have solutions, or what our stability points are, what kind of stability it is. So 5x minus x squared minus x times y equals 0, not comma, dummy, second, 588. And then I want to do -2y, no, -2y, there you go, plus x times y equals 0, comma, squiggly brackets, x comma y, squiggly brackets. Bam! So 5, 0. So by the way, if this is predator-prey, if the one has 0 and the one has 5, the other thing is never going to come back, is it? All right, and then so think about that for a minute. It's pretty interesting. So 2, 3. And 0, 0. I'm here to tell you, friends, if you have 0 predators and 0 preys, this is a very boring problem. Okay? Now, how these things work are exactly the same. Okay? So you're like, oh, they're foxes and wabbits and stuff. Nobody cares. It's just a math problem as far as we're concerned. Okay? In terms of that, but in terms of in reality, obviously, then our x's and y's can only be positive, because it doesn't make sense. Non-negative, I guess. I guess you'd have 0 rabbits, but then they would never really show up, so it's kind of weird. Okay? They don't just spontaneously combust from nowhere. If this is 0, 0, I'm going to start with 0, 0. It's just going to be, I don't need to do this on the calculator. 5, 0, 0, -2, right? And I need to find my stability points for this one. This one's really easy. I can tell you right now it's going to be -5 and +2. And you can see that if you put your minus lambdas in there, you can see where that would end up being that way. But you do what you want to do, and I don't care. Again, if you want to go ahead and make the matrix the other way and then just substitute in, you're more than welcome to. 0, -2. I feel like doing it this way is harder on such an easy one, but there they are. So 5 and negative 2. The point that it's 5 and negative 2 means this baby is a saddle. Which kind of makes sense. That is the idea that here's 0, 0. You're going to kind of come in, you're going to kind of head away from 0, 0. You're going to tend to not go all the way to 0, 0. You plug 2 in there, you're going to get 5 minus 4 minus 3 is 5 minus 7 would be negative 2. And then we're plugging in 2, so that's going to be negative 2. And then 3. And then negative 2 plus 2 is a big fat goose egg. So, you hippie, get over here. Now, I'm just gonna go in and edit this time. I think it's probably easier. But you do what you want. Options. We have options. Spiral sync. Spiral sync. And then, of course, 5, 0. It's going to be negative 5, negative 5, 0, 3. Another saddle. Okay, and again, let's try it this way. I don't know if I can make it work or not. This is too much. It's too hard. It's too hard. Alright, so what do we got here? So 5x minus x squared. Is it minus y? Oh, minus xy. Minus y times x. How about that? Comma. Negative 2y plus xy. Zero, 0 should be a saddle. Sure looks like it's a saddle. That's pretty cool. 5, 0 looks like a saddle. By George, it sure looks like a saddle right there. And at 2, 3, sure looks like it's a spiral sync. It sure does. Ching! We did it. Okay. Now, so that's that. And then you're going to be asked questions like that about. Oops. Question. Oh crap! I unplugged myself. Just a moment. I got too much going on. There's in my little office here, which is kind of crowded. There's electronics and you can shake a stick at. Now, this is again in 6.3. That is problem number we just did. Problem number, where did it go? Yeah, that was problem number 11 through 13. Deal with that one. So number 11 says that show that the coefficient matrix is so that the coefficient matrix of x prime is 5x and negative 2y is at 0, 0 has eigenvalues of 5, negative 2. Well, I literally did that. What I did was I plugged 5 and 0 into here, 5 and 0s into here and here and here, and I got eigenvalues, and the book says confirm that they are 5 and negative 2. Well, they were. I didn't write them down, but they were. That's why it's a saddle point. Okay? And it says number 13 says show that the linearization of 4 at 5, 0 is negative 5u minus 5v, which is basically what I'm saying. And then of course, and then 3v. Now what they're saying is this. It's not really x's and y's anymore, yes, when you take the derivatives. And so when we do those partials, what we're saying is that partial derivative of x prime is going to spit out something that's a function of u's and v's now. So in other words, this is really 5u minus 5v and 0 u's and 3 v's. Okay, so that's what they mean by that. Because technically it's not x's and y's anymore, in that we took the derivative, we just kind of got rid of the constants and the fact that things were x squareds and so forth. Okay, so that's what that means. and then show that it is also a saddle point at 5, 0. Well, I did that. It was saddle point at 5, 0. No. Yes. No, I'm sorry. It was 0, 0 the first time. 5, 0 on number 12. And then on number 13, show that the linearization at 2, 3 was negative 2, and then 3, 0, which we did that just a second ago. And then show that the eigenvalues were negative 1 plus or minus square root of 5i, which is what we also said, which means you have a spiral sink. Cha-ching! We did all of that. Boom, boom, and boom. Okay? Now, interestingly enough, the problem right underneath, right above problem 11 is the phase plane that we looked at, sort of. I mean, it's there, but it's harder to see the saddle points in that picture. Right at 5, 0, you see them crossing. That's a dead giveaway. It's a saddle point. And so at 0, 0, the same thing. But again, a little tricky to see that. Okay? So just be aware that that's what's happening on that guy. Okay? And I would like to turn your attention to on page 1 moment, please. On page 389. Okay, page 389 is a chart that's very succinct about what's happening with all of your eigenvalues. I think for me, if I wanted to know what was going on there, I put a little sticky note there, so check it out, and you'll see what's up. It's a pretty cool deal, and well, kind of fun actually when you do them. Okay, I think I want to do one more just for grins before I sign off for this evening, and it's one that we have not looked at a phase plane of yet. It's going to be just more of a boring one than these last couple. But I want you to see what the phase plane on this guy looks like. Suppose you had the xdt was equal to 3x minus 1, y. Sure. And dy dt is 3y. By George, I think that's what I want. And so it's going to be, I'm going to do 3 minus lambda, and I'm going to do negative 1, and I'm going to do 0, and 3 minus lambda. And so you're like, all right, cool. So then it's 3 minus lambda, and then plus 0. So that's hot. So it's really just lambda is equal to 3, but twice. What happens when you have repeated eigenvalues? What is that? Well, the book says on page 389, if they're the same and they're positive, it's an unstable node or a spiral point. We better go take a look at that guy. So again, I'm going to put in 3x minus y and 3y. By the way, this one will occur at 0, 0. I think that's pretty clear. That's when the whole thing will be 0, is when those are both 0. So 3x minus y, comma, 3y. Blah! Okay? And so what that looks like, it's kind of weird. It's kind of hard to visualize, but that's what's called an unstable node. But the question is it improper? Is it a proper node? And some things like that. So interesting to note. What's happening here is this. Notice how that they're all coming out. You see, they're all coming out from this center point. Oh, shoot. I just hit enter again, I think. But what I mean by this is this. Here's 0, 0. Everybody is, in this case, going out. But they're all going out basically on parallel trajectories. Do you see that? They're kind of coming out like this. But initially, they're coming out kind of parallel. That's that idea, that improper, that unstable deal where it's blowing out, but it's emanating from a source. Okay? And then if you look at another one that's similar to that, like let's look at an improper node. Let's make this a little different. Let's just put an x right here, so that makes this a 1. Okay? And I'm already here, so I'm just going to go plus 1. So we know this is going to be lambda squared plus, or minus 6 lambda, plus 9 plus 1 is plus 10, which that does not factor, but it's going to be 6 plus or minus the square root of, oh, Judas Priest. Make that a positive 1. There we go. Yay. I think it's going to work. Yay, it is going to work. So it's going to be 36 minus 32. It's like I planned it or something. And so it's going to be 6 plus or minus 4, square root of 4, dummy. So 6 plus or minus 2 over 2. So 8 over 2 is 4, and 4 over 2 is 2. So that guy right there, they're both positive, but they're not equal. So that is case number, well, it's partway down the page, where they're both bigger than 0. So let's look at this guy here. So that's going to be 3x plus y. And then x plus 3y. And it's, again, very straightforward. It's going to be at 0, 0 again. But again, look what's happening here. Pow! We're coming off of that thing like that. And again, everybody except the ones that are going straight out like this, they're coming out parallel like that. It's kind of a cool deal. Kind of interesting. Now, if I did the same thing, but I wanted it to come out negative, right? If I wanted that to happen, this would happen, I think. Yes, like so. And let's make one of those negative. And I think it's going to be this, it's going to be that, and then it's going to be that. And so it should be, oh, no. No, I won't leave that alone. Okay. And so it should become that, which is going to give us this. You see? It's going to give us that. So negative 6 plus 2 is negative 4, so that's going to be negative 2. Negative 6 minus 2 would be negative 8 and negative 4. Not same things, right? So, oops, come back. So, make those both negative. So in my function over here, again, just messing with this little bit, all I have to do is change these one little pieces, and it changes how the whole system behaves with one another. Yeah. But again, all about what we changed there. We're changing our eigenvalues and see what's happening. What? Look what happened. It's the same picture, but what? Everybody's coming in, but this time they're coming in, they're swooping in parallel too. Weird. Why is that? Because now if you look at it, I have e to the negative 3t's going on. Or no, that's not true. E to the negative 2t's and e to the negative 4t's, which means everything is crashing down to the 0, 0 point. The previous time they were both here and here, and they were blowing out from that location. Okay? So anyway, feel free on that page 389. I don't know about commit it to memory, but I'd sure put a sticky note there so I could come back to it. I think that's kind of a big deal. And I think it'll help you out as you go along.